Hi everyone, I'm Ferenc. I spend a lot of time actually changing the title backwards and forwards, deciding whether to use AI or machine learning or nothing, but I went with the AI word. The intro actually said that I'm an ex-employee at Boulderton. That's incorrect. I'm still an employee of Boulderton, but I'm spending more and more time with Magic Pony, and actually I'm going to become a Magic Pony employee eventually as of next year. But I'm still here. My job title here is data scientist, and my job title there will be research scientist. So I make sure that I stay a scientist. And so the reason I wasn't sure about whether to use the AI word or not is because many people mean very different things about AI, and I thought I'll just say a few things about this spectrum of things that nowadays you will read about. So on the far end of the spectrum is sentient AI, Nick Bostrom, Elon Musk, or Stephen Hawking, I guess, talking a lot about scary AI agents that will take over the world. There are groups who are thinking about human rights for AI or AI rights for humans, superintelligence, being intelligent than everybody of us, and just generally we are all doomed. On the other end of the spectrum, and I've been there, is data science, and this is, in fact, most of the problems are not machine learning problems, and I learned that myself in my job as a data scientist. It's mostly about databases, actionable insights, as you call it, counting things with things like MapReduce. If any of you used Hadoop or Hive before, you've been looking at hours and hours of just, map and reduce being written on your screen. And so there is a little bit more machine learning, which is like machine learning as a core of these systems, whereas here I would say machine learning would be a nice addition to things. So things like recommender systems using matrix factorization or algorithmic trading, or I would say most of the Kaggle challenges are a little bit more than what you probably need as a data scientist in many situations. And what I'm going to talk about now is roughly there on the spectrum, I would say. So this is modern machine learning and AI, but without actually believing that we are building something smarter than us. I'm going to present machine learning as a new engineering paradigm for building particularly signal processing systems. And crucially, I think AI is sort of justified because now we are building things that traditional approaches, traditional computing has been unable to solve. Lots of vision problems, lots of natural language understanding problems and semantic problems. And this is largely enabled by deep learning. But that's not to say that deep learning is the only way to do these things. So as far as my own personal trajectory, I started out there doing a PhD in machine learning. I was working on Bayesian nonparametrics myself. That was before the deep learning hype. And then I was sort of falling down that way, doing more and more applied things, and ending up as a data scientist here, where I do very little machine learning, if anything. And I'm jumping back there to join the guys at Magic Pony. And the reason why I'm doing this really is this is an applied AI meetup, and the idea was to showcase commercial applications of AI or machine learning or data science. And I think a couple years ago when I finished my PhDs, most of the interesting commercial opportunities were here. This was around the time when Hadoop was a new thing and Spark was an even newer thing. But now I think there are a lot more interesting applications actually that end of the spectrum. So now we can do deep learning has become accessible, and now we understand much better what it's good at. And I think it's actually where most of the interesting applications will happen. So this is the quote. Most of you might have seen it. So Google is restructuring everything around machine learning. The quote says, "Machine learning is a core transformative way by which we are rethinking everything we're doing." So what I'm trying to convince you of is that machine learning is more than just a nice enrichment of your data. It's actually something that you can use to re-engineer complex systems in a completely new paradigm. So trying to use this clicker instead. So the toy example that I'm giving you is image compression. And in the traditional engineering approach, JPEG would be an example. So you start with an image that you want to compress. You want to generate some kind of code representation of it, which is hopefully small. Traditional engineering approach basically says, okay, let's break down this complex problem into series of steps. So first we do, I'm not going to give you a lecture on this, but like discrete cosine transform, quantization, and entropy encoding. So we broke down the process of encoding an image into some subparts, and each of them we understand well as engineers, and we can code this up and we can build hardware to do this. To reconstruct, we just have to invert each of these individual blocks. We know how to redo entropy encoding. It's called entropy decoding. We don't do anything about quantization. That's the lossy part of JPEG. And then the DCT, we know how to invert. That's inverse DCT. And then we get back a slightly uglier version of the image that we started with. This is the engineering approach. In contrast, the machine learning approach, it's not really fair to say that this is a machine learning approach to compression because it wasn't really introduced as one. But this is what it would look like. So we know that we start with an image still. We know that we want to get there. We want to produce a code. But we don't care about how we get there. We just put a big function there. Let's call it the encoder function, which has some parameters that are in there. And with deep learning, this is typically going to be some big neural network with millions of parameters, but it can be anything. And then we also don't know how to invert that function. So let's just put another function called g there. And if we apply this, we encode Spark and then decode it, you'll get this. You'll get something that doesn't look anything like Spark, or at least you have to be a bit tricky to visualize Spark in there somewhere. But what we do now, this is our system. We're not going to touch it anymore, but we say that what we really care about is the reconstruction error. So we compare Spark to the decoded Spark and say, this is not very good. Let's change the parameters, and we get something that looks a little bit more Spark-like, and then something even better, but not quite, until it actually works. And now the reconstruction error is actually not so bad, and the algorithm converged, and the optimization happened, and we are now happy. We now have an end-to-end system that encodes and decodes Sparks. Of course, if we give it more data, more diverse data sets, then it encodes and decodes arbitrary images. Why is this interesting? So again, contrasting it to the engineering approach versus machine learning approach, this is not to say that machine learning doesn't involve engineering. Engineering deals with the how. How are we going to encode this image? Whereas machine learning kind of deals with the why. We just specify the goal of what the method should do, but then don't care about how it's actually achieving that goal. So in engineering, you specify how the system works and break it down into sub-problems. Whereas in machine learning, you specify the goal of the system. You specify the constraints that the system has to satisfy. So for example, how many bits you use in the encoding, and you just add data. And the rest is, so to speak, automatic. And I don't know how many of you are familiar with declarative programming, the term, functional programming, hands up if you are. Okay, I'm going to say this anyway. So I think of machine learning as a declarative way of thinking about engineering complex systems. Whereas the engineering approach, the traditionalism, is a more procedural way of thinking about problems. The reason it's good is because in machine learning, it's easier to improve things because you just improve one of these three things. You either come up with a better objective function, you change the constraints, which would mean, like, for example, using a different neural network architecture, or you just add more data, or you add a different source of data. Whereas to change an engineering system and improve it, that's hard, or at least harder for me, if you have a complex enough system. So, one of the interesting applications, and I try to also convince you that this is commercially also a very interesting application, is visual information processing. And by this we mean pretty much everything that has to do with processing images, processing videos, extracting information from them or transforming it. And I think that the past 2 or 3 years, particularly deep learning, has allowed us to do way more in this space. This was very sophisticated visual information processing was beyond machine learning until, let's say, 5 to 3 years ago, and now it's becoming one of the standard use cases. So I'm going to first talk about compression, which was my toy example, and show you a demo by Magic Pony. And actually, the guys are down there, and they sent me this home video to show you, which is the latest version. So this is running on Rob's iPhone 6S, I guess. And what you're going to see here is contrasting the traditional video encoder or video decoder and the Magic Pony technology, but using exactly the same bandwidth. But the quality difference is going to be the interesting thing here. How do I start this? So you start it, and then this is the standard video codec, and when you touch it, then it suddenly becomes, it switches between the original and the Magic Pony thing. The Magic Pony thing is based on machine learning, and then you can see that if I pause it, not here. So yeah, you could hopefully see that the text is a lot crisper. The text is actually now readable, whereas with the original encoding it wasn't readable. You can even read these little numbers here, which in the previous version it wasn't possible. So you can see the demo actually running on the mobile if you find Rob. Yes. So the other good thing about machine learning is that because you now work in this framework where you just specify the constraints, specify the goals, and add more data to it, it's a lot easier to adopt it to previously unseen situations. Whereas with traditionally engineered systems, coming up with something like the 360-degree video, which is Facebook's feature, like last month, is really, really hard to put new kind of functionality into existing engineering systems. Whereas with machine learning, you kind of just change the input and the output of the algorithm. It's a little bit harder than that, and it also involves a lot of engineering. But it's generally speaking a lot more flexible in terms of accommodating new unseen data types. So a lot of things are happening in the video compression, video encoding space around 360-degree video, AR content, and virtual reality content. And that's actually something that the traditional technology is really struggling to keep up with. Another interesting set of applications is computational photography. And I'm gonna try to convince you that photography is also about machine learning. My whole life is about machine learning, in fact. So the more classical examples of this are image deblurring. So you have a blurry image, and then you apply machine learning, which learns to undo the effects of motion blur, and then you get a relatively crisp image. And this is out of Stefan Harmeling's lab in Tübingen. So this is not actually our work. Image denoising is also with a relatively simple machine learning method, which is on the right-hand side. You can beat the state-of-the-art, which is BM3D, which is years of engineering, and it's actually a pretty slow method for denoising. This one was really super simple to do. You just put a neural network between the noisy image and the clean image, and you added lots of data, and it will learn a transformation like that. Now, of course, to improve that any further, that's hard, and you have to be slightly cleverer than that. But it really shows that with machine learning, you can catch up with years of engineering progress. Another example of new data types and machine learning being able to adopt, this is a camera which has 16 cheap imaging sensors. The idea being that it's really hard to improve your iPhones or smartphones' camera performance because the size is limited, the quality of the materials is limited. But nobody told you that you can't put 16 of them in the same package. And now every time this camera takes an image, 10 out of the 16 cameras will actually take a picture. And then out of those 10 sensor images, the system somehow stitches together one high-quality image. So that suddenly becomes an inference problem. That suddenly becomes a machine learning problem. And photography is becoming more and more a software problem or a signal processing problem, and not so much a how do we build better sensors problem. This is a pretty interesting new possibility that machine learning allows us to do, and you've probably seen this on Reddit and a bunch of other places. I call this computational creativity, but this has to do with anything where the machine is actually generating some interesting things that weren't there before, or yeah, it's the generative models is the technical term for this. One example here is texture generation. So you give the method a real texture, in this case this bunch of onions, and then it will generate a synthetic one which looks like this. So if you look carefully, you can see that these are not actually onions. So the method didn't actually understand that it should do something with onions, but it looks roughly like that. And in this case, it actually works amazingly well. So you give it this as a source image, and you ask the method to generate a similar looking texture, and it generates this. And I think I would be hard pressed to actually tell the difference between these two. So this is pretty amazing. And you can see that it also has drawbacks. So if you do anything which has regular patterns or periodicity, this particular method doesn't work particularly well, although it's being improved probably as we speak. This is also from Tübingen in Germany, Matthias Wertge's group. This you're more likely to have seen. It's basically taking something, a style image, which is going to inform what style we want the image to be. You take a content image, and the algorithm generates a mashup where you use the style from the first image, and then you use the content from the second image, and you generate this. And if you look on the internet, you will find lots of crazy examples of this now. There is even a service online where you can upload your own photo and choose your style, and then in a couple of days' time, they will generate an image like this. And it's already taking our jobs. This is two friends of mine who had a wedding a couple of weeks ago, and this was my wedding present to them. This was in Matisse style, one of their Facebook photos, actually. And the last application, which is increasingly interesting because of augmented reality and virtual reality, perhaps, is inverse graphics. So this is when we look at an image and we want to reconstruct the three-dimensional world from just a single image. And it's pretty simple if you have stereo images. So if you have two cameras, like in the Kinect, well, I say pretty easy, it's easier. But if you only have one single image or one single video, reconstructing the 3D structure from that is actually really, really hard for computers to do. It's very easy for your brain to do. This is very recent, out of the MIT Media Lab. So the input to the system was just a normal soccer footage, and the output is this 3D footage, which is obviously displayed in this funky 3D glass way. So essentially it takes the input and the data from the normal footage, and it can turn it into a 3D TV content. So if you have any old DVD which has some content, this algorithm could theoretically turn that into 3D TV content, which is actually pretty interesting use case. This one is a similar thing, and I put this here because this is showing very clearly the connection between machine learning and the declarative way of thinking about problems. This is a programming language called Picture, in which essentially you program a random process which generates a three-dimensional object. For example, one like this. So you say that objects in the real world look like this, and you program a random number generator based program that will generate likely objects that you think you will see in the visual world. And then once you've done that, the algorithm will then see to take an image as an input, in this case this beer bottle, and over time figure out, so this is kind of the system making inference. Initially it thinks that the object looks like this, but as it keeps thinking, you will have a better and better, more refined idea about what this object looks like until it actually ends up with the right shape. But the whole point here is that, again, in picture, you don't specify how this process works. This bit, the figuring out bit, is all automatic. All you need to specify is this prior bit, which describes what you think are likely shapes to occur in real world. And the rest of it is automated. So, in summary, I talked about my interpretation of AI. In signal processing, it's not just a nice addition to what we are doing, but it's actually, I think, a paradigm shift, and it's actually a new way of creating very complex systems. This creates a lot of interesting opportunities. A lot of the typical applications of visual information processing are turned upside down. So I talked about compression. You can make it much better if you use machine learning. Computational photography. Photography is increasingly, I think, a machine learning visual information processing problem rather than a sensor problem. It also enables new applications, which the traditional engineering approaches will have a hard time catching up to. So computational creativity is something that's only possible recently. We don't quite know what it's going to be used for, but we have a couple ideas. And then inverse graphics for augmented reality and scene interpretation is also something where we've seen pretty huge breakthroughs in the last couple of years. Thanks. And I don't have a we are hiring slide, but James just asked me last minute to say that Balderton's portfolio companies, that companies we invested in, including Magic Pony, are always hiring. So if you are thinking about a career move and you want something high profile, chances are you work with the company that would be your next best career move. So get in touch with James or myself. And this is myself selling out, and it's up to you for questions. Thanks very much.
Given the speed of change there, how does someone who's working in machine learning or an AI-enabled company maintain a competitive advantage?
So I'm not sure if that was on. So the question was, how does a company maintain competitive advantage because the field is so fast changing? I think it all boils down to people and talent, in my view. So having the best team possible in AI is probably puts you in a pretty good competitive position against others. And it's also, a lot of these breakthroughs have happened not just because the machine learning has changed so much, the theory that we use just changed so much, but because people have figured out how to run these things on GPUs, people have figured out how to use way more data, and the fact that we need to use way more data. So I think it's a lot more about these breakthroughs are happening so fast because of the convergence of multiple things. And if you have studied machine learning 5 years ago, you would probably still understand everything that's going on today in the field. It's just that we're using a lot more data, and we're using a lot more computational resources mostly.
How the kind of the hard work has now shifted a little bit from what we were doing. So previously, it was an engineering problem, and someone like I or anyone else would write the encoding algorithms for, processing images and things like that. And now in a declarative world, in an AI machine learning world, the hard work is somewhere else. Where is the hard work now? Where are you putting in the time, and where is everyone else putting in the time?
So the question was now that if machine learning is a more declarative way of thinking, where are we putting in the time? I think what I said was a very rosy picture about how machine learning actually works. And of course, There's a lot of thought going into finding the right architecture. If you work just within the scope of neural networks, it's figuring out what kind of neural network you want, how many layers do you want, and these kind of things. That's something that requires a lot of expertise and also the technical, theoretical understanding of what you're doing. So I think a lot of the time is being spent on mastering that. So that's more like a research process, trying different things. The same applies to things like loss functions, trying out different things and seeing which one works best. It's a little bit of a trial and error. But the other way to answer this question is that the same kind of movement towards declarative ways of thinking about problems also happened in data science, where 5 years ago we engineered systems that did parallel processing of large data sets, and now people just use the Spark API and actually just say, I want to run this function across my entire data set, and then how it's actually done is abstracted away. So I think that this is the way by which I meant that machine learning is kind of declarative in the same way.
Yeah, that was really interesting. I think there's so many great examples out there about machine learning and neural networks producing all these beautiful best case examples. I'm quite interested in how do you control the worst case, because you also have these galleries of sort of fooling neural networks, right? Where you have images and they see something or they think they see something which is way off. So if you come up with these, say, compression algorithms, right? You come up with a lot of really nice best cases. How do you get an idea of what the worst case is? How can you control that it doesn't go completely nuts for a given input? Does that make sense?
Yeah, so the question was, how do you actually understand the worst cases? I don't think that's a problem that's specific to machine learning, because we work in a subfield of signal processing. I think the same would apply to other kinds of signal processing. For example, in JPEG world, you kind of understand what are the artifacts that your method will introduce, so you can actually think about, what is the worst possible thing that I can try and encode that'll look pretty ugly on the output. And that's probably going to be something like text or something like lines, like a diagonal line or something like that. You now have better diagnostic tools for neural networks specifically that are essentially using optimization-based methods to find these worst cases. So for classification, I think you're referring to the fact that you can take an image that clearly contains a dog and the neural network says it's a dog. You can add a little bit of noise, which is not perceptible to a human, and suddenly the network thinks it's an ostrich or something like that. And actually, we are developing as a community these diagnostics tools that will allow us, via optimization, to find the worst case scenarios. And I think these diagnostic tools will evolve over time, and clearly it doesn't cover all the cases, but you will be able to say, at least, show me an image within my data set even, where the output is actually the worst, and then you can eyeball those images and maybe understand a little bit about why that might happen, or what can you actually do about it.
I actually come from an image processing background. I was writing exams on image processing sort of pretty much this time last year. First thing that struck me was you didn't use Lena for any of your images, which is quite, I guess you chose Spark because it's new age. But how easy is it to translate a model generated with the methods you've described into hardware? So I think engineering solutions for a long time, it's been about optimizing not only the computational stuff, but putting it onto chips so that it can be used in the real world. Is the same process happening in your field?
Yeah, I think the good answer to that is that you don't necessarily need to anymore. So for example, the demo that I showed you, the home video of the demo that I showed you, is running real time on the iPhone, actually using the hardware on the iPhone, which is general purpose computing hardware, and GPUs and stuff like that. And now, not only are these GPUs and other processing things on the device more capable, but they also are more energy efficient. So you can actually run this thing without blowing up the phone real time and without immediately killing your battery. So the reasons for developing custom hardware, there's less and less reasons for that. And particularly for mobile, it would be really, really hard to develop a new kind of customized signal processing chip and try to get it into an Android phone. That would be only a handful of companies who would try to do that, but probably even they would go for more generalized solutions. That said, and also in applications like self-driving cars, NVIDIA has this onboard GPU-based unit which is doing all of the AI neural network calculations. So everything is moving towards this general purpose hardware, and they are becoming cheaper, they are becoming more energy efficient, and they are generally more efficient. I think that some companies like IBM that I know of are working on FPGA implementations for neural networks, and some of those might be relevant for some applications, but probably not for things like consumer tech that you want to put into a mobile device.
Cool. Well, thanks very much.